Hello there, and welcome to this sleepy corner of deep time. I'm really glad you found your way here tonight. Wherever you are listening from, a small apartment in a restless city, a quiet room by the sea, or a bed lit only by the soft glow of your screen, this little stretch of time is just for you. A pause between everything that happened today and the dreams that are waiting for you on the other side of sleep. Tonight, we're going to drift together into one of Earth's most haunting and strangely comforting stories. A story not about one ending, but five. Long before humans ever walked under the stars, before mammoths, before dinosaurs, even before forests the way we know them, life on Earth had already been nearly erased. Not once, but again and again. Entire oceans went quiet. Forests turned to ash. The sky itself changed color. Whole branches of the tree of life snapped off in what, geologically, was almost a single breath. We call these events mass extinctions. Moments when at least 3/4 of all known species vanished from the planet in what, to rocks and fossils, counts as suddenly. But hidden inside those endings is something else. Survival. Because somehow, every single time the world collapsed, something held on. Tiny, overlooked creatures in deep water, small animals burrowed into the soil, patient microbes drifting through dark oceans. They became the quiet architects of everything that came next. Of forests, of dinosaurs, of mammals, of us. So tonight, we're going to follow that thread. We'll drift down through the rock record, reading the stories pressed into stone. We'll visit ancient oceans that froze, reefs that suffocated, skies burned by volcanoes, and the night the dinosaurs' age ended in a single flash of light over what is now the Yucatan Peninsula. We'll ask gentle, unsettling questions. Why did some worlds end while others began? Why do small, flexible, ordinary creatures so often inherit the future? And in our time, as scientists warn, we may be entering a sixth mass extinction. What can these old disasters quietly teach us about resilience, about limits, and about the choices we still have? For now, you don't need to remember any numbers or names. You don't have to solve anything. All you have to do is let your shoulders soften, notice the rise and fall of your breath, and imagine the ground beneath you, made of stones that remember every age the Earth has ever lived through. You are lying on a planet that has survived firestorms, frozen seas, poisoned air, and 5 great collapses, and is still here, carrying you through space tonight. So, if you're comfortable, close your eyes, or let your gaze soften. Let the day fade to the edges of your mind, and together, we'll begin our slow journey through all 5 mass extinctions, and how life, somehow, survived. Chapter 1. Reading Extinction in Stone. If you could hold a piece of the Earth's memory in your hand, what would it look like? Not a photograph, not a video, just a quiet, ordinary-looking rock. Imagine one of those rocks now, resting in your palm. It feels cool, solid, unchanging, but inside it, layer by patient layer, is a story that took hundreds of millions of years to write. A story of oceans that rose and vanished, forests that bloomed and burned, strange creatures that appeared, thrived, and then were gone so completely that only their outlines in stone remain. This is where our journey begins tonight, not with dinosaurs or asteroids, but with the rocks themselves. Because to understand mass extinctions, these rare, world-shattering events when most life disappears in a geological blink, we first have to learn how to read the Earth's diary. Not the one written in ink, but the one pressed into mud, turned to stone, and hidden beneath our feet. As you listen, you might let your attention soften a little. Notice your breath, the gentle rise and fall of your chest. Let your thoughts move slowly, like sediment settling through quiet water. Scientists have a name for the ordinary, ever-present rhythm of species disappearing over time. They call it the background extinction rate. Even in a healthy, stable world, some species always fade away, outcompeted by others, nudged aside by climate shifts, or simply unlucky over long enough stretches of time. A few vanish every 1,000 years, and new ones arise to take their place. If you could watch life on fast forward, it would look like a slow, shimmering drift. Forms changing, branching, fading, reappearing in new shapes. That's the background. The quiet ticking of evolution's clock. A mass extinction is not that. A mass extinction is when the clock shatters. By definition, a mass extinction is a global event where at least 75% of all species disappear in what geologists consider a short interval, sometimes over hundreds of thousands of years, sometimes far less. To us, that sounds impossibly slow. But to the deep time of the Earth, it's almost instantaneous. A sharp drop, a cliff, entire categories of creatures vanish. Reefs collapse, forests go silent. The diversity of life, all the colors, shapes, and sounds that define an age, are cut down at once. How do we know this happened? If no one was there to see it, we know because the Earth keeps records. Picture a calm, shallow sea hundreds of millions of years ago. Soft mud accumulates slowly on the sea floor grain by grain. Year after year, tiny shells settle into it. The remains of trilobites, corals, early fish, and drifting plankton all become part of the sediment. Over long stretches of time, the mud compacts, hardens, and turns into sedimentary rock. That rock is a page. And if you were to slice down through the layers of that seafloor, like cutting through a many-layered cake, you'd see time stacked on top of itself, oldest at the bottom, newest at the top. Some layers are rich with fossils, little shapes everywhere, coiled shells, branching corals, fragments of skeletons. They tell us that life was flourishing when that layer formed. Then, above them, suddenly, almost nothing. A band of rock that is strangely empty. A few scattered fossils, or none at all. It's like turning from a page full of text to one that's nearly blank. That sharp change from abundance to absence is one of the most important clues that a mass extinction has occurred. The creatures didn't slowly fade out. They stopped. So many, all at once, in a way that normal background extinction cannot explain. To the trained eye of a paleontologist, these rock cuts aren't just shapes and colors. They're before and after, alive and erased. But fossils alone are not the only evidence. The Earth hides more subtle clues in its chemistry. Inside each layer of rock are tiny variations in elements and isotopes, different forms of atoms with slightly different weights. By measuring them, scientists can reconstruct the conditions that existed when that rock was forming. A spike in iridium, a metal rare in Earth's crust but more common in asteroids, can hint at something that fell from the sky. A sudden change in carbon isotopes can reveal that something disturbed global photosynthesis. Ancient forests dying, oceans going still, or vast blooms of microbes briefly taking over. Shifts in sulfur and oxygen can speak of anoxic seas, waters starved of oxygen, where fish suffocate and only bacteria thrive. All of these chemical signatures are like fingerprints. When they line up with the sudden disappearance of fossils, we begin to see not just that a mass extinction happened, but how. Was it cooling, warming, poisoned oceans, fire from inside the Earth, or from far beyond it? The rocks don't answer in sentences, but they whisper patterns. And as scientists read more and more of these rocky pages from all over the world, a pattern emerges. Not just one catastrophe, but several. In some intervals of deep time, life is rich and varied. Reefs build vast undersea cities. Forests stretch from horizon to horizon. Strange creatures fill every niche. Then, at certain boundaries, those rich communities drop off sharply. Not just in one place, but across multiple continents, in different environments, at different depths. The same story, repeated in many accents. This is what some researchers call an extinction rhythm. Not a perfect, predictable beat, but a recurring pattern. Boom. collapse, recovery. Diversity rises, holds for a time, and then plunges. The Earth is not a gentle, unbroken climb from simple to complex. It surges, stumbles, starts again. If you listen closely to the fossil record, those plunges are loud. They're the moments we call the Big Five, the 5 great mass extinctions recognized so far in Earth's history. Each one left scars in stone, each one erased worlds, and each one forced life to reinvent itself. You might notice, as you lie there listening, that your own life has smaller versions of these rhythms. Times when things felt stable, familiar, full of detail, and times when something shifted suddenly, and the landscape of your days looked different overnight. Endings and beginnings, pauses and rewrites. The Earth has been doing this for over 4 billion years. What makes the Big Five extinctions so extraordinary is not just how devastating they were, but how much they changed what came after. Without them, the history of life would be unrecognizably different. Different oceans, different forests, perhaps no dinosaurs, perhaps no mammals, perhaps no us. Tonight, we'll meet each of these crises in turn. We'll visit icy Ordovician seas, suffocating Devonian oceans, the burning world of the Great Dying, the volcanic scars of the Triassic, and finally, the night a small asteroid ended the age of dinosaurs. But we'll do it slowly, gently, because this isn't a story about doom. It's a story about persistence, about how, against unbelievable odds, life kept finding narrow paths through chaos. And as we turn from this first chapter of stone and silence into the next, we're going to travel very far back, farther than dinosaurs, farther than forests, to a time when almost all life lived in the sea, and the world's first great ending arrived as ice. Chapter 2: The First Collapse. Frozen Seas of the Ordovician. Close your eyes for a moment, if that feels comfortable. Let your imagination sink downward, beneath the soil, beneath the bedrock, down into a world that no longer exists. It's about 444 million years ago. The land is mostly bare rock, dust, and wind. A few tiny plants and moss-like patches cling to damp edges, but there are no forests, no grasses, no birds in the sky. If you were standing on a shoreline and looked inland, the world would feel strangely empty. But if you walked into the water and slipped beneath the surface, everything would change. The seas are where life lives. Shallow oceans wrap around low-lying continents like a warm, sunlit band. The water is clear, full of drifting plankton and tiny particles that glitter in the light. On the seafloor, early coral reefs spread like underwater cities, built not by modern corals, but by ancient reef builders now long gone. Trilobites, armored, many-eyed scavengers crawl over the sediments, their jointed legs leaving delicate tracks behind them. Nautiloid cephalopods, distant cousins of today's squid and octopus, glide through the water in long, straight, or gently curved shells, like living torpedoes. Brachiopods and bryozoans anchor themselves in dense colonies, filtering nutrients from the water. Crinoids, stemmed sea lilies, sway like flowers rooted in stone, catching drifting food with feathery arms. This is the Ordovician world, and almost all of its richness is underwater. For millions of years, this marine realm is stable and flourishing. Life experiments cautiously, branching into new forms, filling new niches. The continents are mostly gathered in the southern hemisphere, forming the ancient landmass of Gondwana. Climate is generally mild and warm, especially in those extensive, shallow seas. And then, slowly, at first, something begins to change. Far from where the trilobites crawl and nautiloids drift, high above the waves and across the distant polar regions, the air begins to cool. It's not a sudden snap of winter, the way we experience seasons, but a slow, long exhale of the planet itself. Over hundreds of thousands of years, temperatures inch downward. Snow falls in the high latitudes and doesn't melt. Layer upon layer of snow compresses into ice, and ice into enormous glaciers. On the southern part of Gondwana, ice sheets grow and spread, bright and reflective, bouncing sunlight back into space, instead of letting the Earth absorb it. The more ice there is, the more the planet cools. The more the planet cools, the more ice forms. A feedback loop has begun. But this cold does something else too. Something more subtle and devastating for life in the seas. It locks away water. Every new meter of glacier is water that used to be in the ocean. As the ice sheets expand, sea levels begin to fall. The warm, shallow continental shelves, those sunlit nurseries where most Ordovician life thrives, are exposed, bit by bit. Reefs that were once comfortably submerged find themselves closer to the surface, then at the surface, then suddenly stranded in air. Imagine an entire thriving reef, full of movement and color, slowly lifted out of the water over centuries, as if the ocean itself were draining away. To the creatures anchored in place, it would be a catastrophe spread out just long enough to be inescapable. As sea levels drop, the shape of the oceans changes, coastlines shift, currents adjust. Water that once flowed over wide, shallow platforms now pours into deeper basins. Temperature patterns change. So do oxygen levels. Many of the Ordovician organisms are specialists, finely tuned to narrow ranges of depth, light, and chemistry. They live in clear, stable, well-oxygenated water. As the shelves shrink, their world shrinks with them. Some can retreat a little deeper, following the water downward. Some are carried to new regions by currents, but many are rooted, or slow-moving, or simply too sensitive to tolerate the new conditions. They begin to disappear. At the same time, tectonic plates, the great slabs of crust that move slowly over the Earth's mantle, continue their long, patient drift. Continents shift positions, altering global circulation patterns even further. As Gondwana moves across cooler latitudes, the climate continues to favor glaciation. The planet is rearranging its own thermostat, and life, which had filled the seas so confidently, finds itself caught in the middle of a system-wide reconfiguration. There is another quiet player in this drama: the first land plants. During this time, tiny, simple plants have just begun to spread onto damp soils and coastlines. They're not trees or tall ferns yet, just low-growing forms that cling close to the ground, drinking in water and light, and slowly pulling carbon dioxide from the air. Individually, they are small, but over millions of years, together, they start to change the atmosphere. Carbon dioxide is one of Earth's main greenhouse gases. It helps trap heat and keep the planet from being an ice ball. As early plants photosynthesize, they draw down this carbon, releasing oxygen in return. Some of that organic matter ends up buried in sediments, locking the carbon away. The more plants grow, the more CO2 is removed. The more CO2 is removed, the more the planet cools. The more the planet cools, the more ice forms. Plants, in their own quiet way, are helping drive the world into an ice age. They're not malicious. They're just doing what life always does, taking the available energy, using it, and changing the environment in the process. But for marine life balanced delicately on the edge of the continental shelves, the result is the same. The water retreats, the temperatures shift, and the habitats disappear. By the time this Ordovician glaciation reaches its peak, sea levels may have dropped by more than 100 meters. Shallow seas turn into exposed mudflats and new land. Coastal habitats contract into narrow strips. Many species simply have nowhere left to go. The fossil record from this time shows a dramatic collapse. Up to 85% of marine species vanish. Trilobite lineages that had survived for tens of millions of years end in tight, sudden bands of rock. Reef-building organisms decline sharply. Brachiopods, graptolites, and many other groups suffer heavy losses. In some layers, the once rich fossil assemblages are replaced by simple, dull mudstones, with only a few traces of life. It is the Earth's first known mass extinction, and yet even here, even now, not everything is lost. Because while the shallow seas are battered and drained and chilled, the deeper waters remain more stable. Temperatures change less dramatically there. Light never reached these depths, even in better times, so its loss is not as important. Some currents still flow. Some oxygen still circulates. In the dim, quiet zones beneath the surface chaos, life continues. Tiny plankton and soft-bodied invertebrates find refuge in deeper or more sheltered basins. Generalist species, those able to tolerate a range of conditions, survive where specialists fail. Some organisms adapt gradually to the colder water, to the altered chemistry, to the new patterns of upwelling and sediment. For them, the extinction is still a crisis but not a final one. This concept of scattered safe pockets where life hangs on during global collapse is so important that scientists have a name for it: refugia, little refuges, lifeboats in a drowning world. They might be deeper parts of the sea, shielded from rapid temperature swings. They might be certain latitudes where conditions stay moderate. Later in Earth's story, they will be deep valleys, cave systems, or isolated wetlands. During the Ordovician crisis, these refugia become the seed banks of the future. The species that manage to survive by luck, by flexibility, by simply being in the right place, with the right tolerances, carry with them a smaller, narrower sample of life's diversity. The rest has been lost. This narrowing is called a genetic bottleneck, when a once rich population is reduced to a tiny remnant, and all future generations must descend from that small group. It's like burning an enormous library and being left with only a handful of books. The stories that remain will still be rich, still full of detail, but many possible stories are gone. In the millions of years that follow, the ice eventually retreats, the glaciers melt, sea levels rise again, warmth returns to many regions. The shallow seas flood back over the continents, tracing old paths and making new ones, but they do not refill with the same communities they lost. Life returns, but it returns changed. Reefs are rebuilt, but by different combinations of organisms. Trilobites survive, but in a reduced and altered set of forms. New groups begin to diversify, taking advantage of open ecological space left empty by extinction. Complex ecosystems, like coral reefs and intricate food webs, take a long time to rebuild. For a while, the oceans are simpler, their communities thinner, their interactions less elaborate. But slowly, over tens of millions of years, diversity climbs again. From this first great collapse, evolution learns certain lessons not consciously, but through the quiet filter of survival. And one of those lessons is this: being widespread is safer than being confined. Being flexible is safer than being specialized. Being small and adaptable can be more powerful, in the long run, than being large and perfectly suited to a narrow niche. These lessons will be repeated, over and over, in every extinction that follows. As you rest here, listening to the story of that long-vanished ocean, you might notice how calm your own inner sea has become. The details of names and dates aren't important. What lingers is the feeling of an ancient world changing slowly, then suddenly, and somehow recovering. The Ordovician extinction was the first time Earth cut away so much of its own living fabric at once, but it would not be the last. Already, even as new species begin to spread through the renewed seas, a different kind of crisis is quietly forming in the background. Plants are climbing higher, forests are beginning to rise, rivers carry more nutrients to the ocean. Far ahead in time, another mass extinction, the Devonian, will arrive not as a single blow, but as a long unraveling. This time, the seas won't freeze, they'll suffocate. And in our next chapter, we'll drift into that slow, choking world, and watch how life, once again, finds ways to slip through the cracks. Chapter 3. The Long Drowning. Oceans Without Breath. Devonian Extinction. Imagine yourself drifting gently through warm, shallow water, Sunlight slips through the surface in trembling ribbons. The seafloor is covered in coral-like structures, delicate and branching, and among them swim bizarre early fish, many armored, many toothless, some with strange jawless mouths shaped like shields. It is the Devonian period, about 375 million years ago, a time often called the Age of Fishes. And for good reason. Life in the oceans has never looked quite like this before. Early sharks glide through the water, streamlined shadows with toothy grins. Placoderms, the armored titangent fish of the ancient seas, move like floating tanks, their bony plates glinting as they hunt. Lobe-finned fish, chunky and muscular, slip between reefs with slow confidence. Some of them will one day crawl onto land and become ancestors of every amphibian, reptile, bird, and mammal to come. Even the plankton bloom in dazzling abundance, their tiny shells swirling endlessly, catching the light like drifting sparks. But this world, glowing with possibility, is beginning to dim. Not quickly, not loudly, but slowly, subtly, like a candle burning down over centuries. The Devonian extinction isn't a single event. It isn't one shock, one asteroid, one volcanic burst. It is a drawn-out unraveling, a long suffocation of the seas that will last for millions of years. To understand how it begins, picture something surprisingly humble: plants. During the Devonian, life on land is experiencing a revolution. Plants, once tiny, moss-like patches clinging to damp ground, have evolved into towering forests. Giant ferns and early trees rise upward, spreading vast roots into the soil. With deep roots comes something new: the breaking down of bedrock, the release of minerals into rivers, and the slow delivery of nutrients into the oceans. On its own, this is not harmful, it is natural. But combined with flourishing plant life, it begins a chain of events that the oceans cannot tolerate. Plants draw carbon dioxide from the atmosphere, just like modern forests do. They fix it into their tissues, lock it into roots and leaves, and when they die, much of that carbon becomes buried. As forests spread across the continents, atmospheric CO2 levels fall. With lower CO2 comes global cooling. Temperatures drop, weather patterns shift, cold water sinks in the oceans, altering circulation. At the same time, nutrient-rich sediments wash into coastal seas, feeding enormous blooms of algae. For a while, the oceans become strangely lush in the shallows, too lush. When these algae die, their remains rain downward, where bacteria decompose them. But that decomposition uses oxygen, and the more decomposition that occurs, the more oxygen is stripped from the water. Slowly, subtly, a deadly boundary begins to form in the depths, a line below which there is no breath, no oxygen, no life. Scientists call these regions anoxic zones, dead zones. As they expand, fish populations weaken, coral-like structures wither, trilobites, which have survived since the Cambrian, begin to decline. Reef ecosystems, which took millions of years to build, start collapsing into barren plains. Still, life tries to adapt. Many fish move into shallower waters. Some species shrink. Others shift diets or reproduce more often. But the anoxic zones keep spreading. This first wave of suffocation should have been warning enough. But the planet is not done yet. In the late Devonian, massive volcanic eruptions in Siberia and possibly elsewhere release pulses of carbon dioxide, methane, and sulfur into the atmosphere, destabilizing the climate even further. Temperatures swing. Sea levels fluctuate. Oceans stratify, warm layers floating above cold ones, preventing mixing. The deeper water becomes stagnant, dark, poisoned. Entire food chains collapse quietly. From the bottom upward, plankton disappear. Filter feeders starve. Predators lose their prey. The great armored placoderms, once kings of these seas, vanish forever. It is not a single dramatic day, not a violent crash like the one that ended the dinosaurs. It is decades upon decades of ecosystems trying, failing, and trying again until there is nothing left to try. In the rocks of this time, there is a strange black layer, a layer of organic rich shale, thick with the remains of countless dead organisms. It forms only when whole seas become so anoxic that nothing can decompose properly. It is the rock record of a world that drowned in its own breathlessness. Yet, even in this long collapse, life finds cracks to slip through. Small, unremarkable creatures, generalists, scavengers, soft-bodied organisms hide in shallow pools, coastal wetlands, or temporary refuges where oxygen still trickles in. Some fish develop stronger lungs and spend more time near the water's surface. A few lobe-finned fish venture onto land for safety, beginning the slow transition toward amphibians. Once again, the survivors are not the enormous, the armored, or the elegant. They are the flexible, the patient, the ones able to endure long stretches of scarcity. When the extinction finally ends after millions of years and multiple pulses, up to 75% of species are gone, but the forests that triggered the crisis remain, and in their shade, something new begins to stir. The earliest true tetrapods, creatures with limbs sturdy enough to walk. Extinction removed the old rulers of the sea, but in the quiet wetlands, the future rulers of the land are being shaped. As you breathe gently, perhaps you can feel the rhythm of this chapter, slow, drawn out, quietly suffocating. Not every ending arrives in fire. Some arrive as a long silence. And from that silence, we will now travel into fire, the largest, most devastating extinction the Earth has ever endured. Chapter 4. The Great Dying. When the world became a furnace. Permian extinction. If the Devonian extinction was a long, suffocating fade-out, the Permian extinction was a world-shattering crescendo. It is the closest Earth has ever come to becoming truly uninhabitable. This is the Great Dying. 252 million years ago, an event so vast and catastrophic that it erased over 96% of marine species and 70% of land vertebrates. Nothing else in Earth's history compares. To understand it, imagine a world that begins warm, lush, and full of possibility. The continents are united in a supercontinent called Pangaea, a single massive landmass stretching from pole to pole. It is surrounded by a global ocean, Panthalassa, where fish, ammonoids, early sharks, and strange sponge reefs thrive. On land, forests of conifers and seed-bearing plants rise. Reptiles, amphibians, and mammal-like creatures walk through fern-filled valleys. Giant insects hum through warm, oxygen-rich air. Life is rich, diverse, confident, and then the planet cracks open. In what is now Siberia, the Earth releases a fury unlike anything before or since. The Siberian traps eruptions. For hundreds of thousands of years, fissure volcanoes pour out lava not from mountains, but from long gashes in the crust. The lava fields they create cover an area larger than Western Europe. But it isn't simply the lava that kills. It is what the lava brings with it. Volcanoes release carbon dioxide in unimaginable quantities, methane from destabilized permafrost, sulfur dioxide, causing acid rain, halogen gases, damaging the ozone layer, particulate ash, dimming sunlight, toxic metals, poisoning rivers and soils. Every system begins collapsing at once. CO2 traps heat, driving global temperatures upward by as much as 10 degrees Celsius. Methane, a far more potent greenhouse gas, accelerates the warming. Sulfur clouds trigger acid rain that burns through forests and soils. Ozone depletion exposes the surface to lethal ultraviolet radiation. This is a planetary cascade failure. Forests die. Oceans heat. The atmosphere collapses into chaos. Marine life suffocates as warm water holds less oxygen. Anoxic zones spread, just as they did in the Devonian, but now on a global scale. As oxygen levels drop, sulfur-loving bacteria take over, releasing hydrogen sulfide, a gas poisonous to most life. The oceans turn into chemical nightmares. On land, drought spreads. Rivers shrink. Reptiles and amphibians fall into steep decline. Microbial soils expand, turning once lush valleys into barren wastelands. The fossil record shows scenes of a planet unraveling, forests turning to ash, reefs dissolving into empty mud, creatures gasping in shrinking lakes, whole ecosystems collapsing layer by layer. And when the skies finally clear, the world left behind is unrecognizable. For hundreds of thousands of years after the Great Dying, life is sparse. Ecosystems are simple, fragile, and quiet. Where forests once stood, there are fern fields. Where coral reefs once towered, there is barren seafloor. Where complex food webs once thrived, only a few hardy generalists survive. Recovery is slow, so slow that scientists describe the early Triassic as a disaster world, filled with low-diversity communities. But in the cracks of this devastation, something new begins to form. Tiny burrowing animals survive in soil pockets where temperatures were moderated. Microbes rebuild the chemical cycling of the earth. And reptilian survivors, small, fast, adaptable, begin to diversify. Among them is a group that will one day change the world. The archosaurs, ancestors of crocodiles, pterosaurs, and eventually, dinosaurs. The Great Dying burns the world to its foundations. But from the ashes, the seeds of future giants are planted. Tonight, as you rest here listening, imagine that burned and barren earth. Imagine the silence after the fire, the oceans still, the forests gone, only the wind moving across empty plains. And imagine, in that silence, a single burrow. Inside it, a small creature breathes. It has survived what almost nothing else did, because extinction, for all its terror, always leaves someone behind. Someone small, someone adaptive, someone ready to begin again. And in the next chapter, we move into that rebuilding, into the rise of dinosaurs, and the next great reset that shaped the world we know. Chapter 5: Fire in the Rift. The Triassic extinction and the dawn of dinosaurs. The Permian extinction ended millions of years before the next great catastrophe. In that time, life struggled upward from the ashes, fragile but persistent. The early Triassic world is harsh, hot, dry, unpredictable. Many species live near their physiological limits, constantly pushed by climate swings and unstable ecosystems. But slowly, stubbornly, nature finds balance again. Forests return, rivers flow steadily, amphibians creep back into wetlands, reptiles diversify into new forms. Among them are the earliest dinosaurs, but they are small, swift, and unremarkable at first, overshadowed by larger reptilian rivals. For tens of millions of years, the world teeters between recovery and fragility. And then, the ground begins to tear open. The supercontinent Pangaea, stressed by internal forces, starts cracking apart. Deep rifts form across what are now North America, Africa, South America, and Europe. These rifts flood with magma. The region becomes what scientists call the Central Atlantic Magmatic Province, one of the largest volcanic events in Earth's history. As with the Siberian traps, lava is only the beginning. Gases rise, carbon dioxide, methane, sulfur, temperatures spike, acid rain returns. The oceans warm rapidly. Oxygen disappears from vast stretches of seafloor. Once more, life begins to unravel. Plants wilt under chemical stress. Amphibians decline again, their delicate eggs easily damaged. Marine reptiles vanish. Early mammals lose many of their lineages. This is the Triassic-Jurassic extinction, wiping out about 75% of species. But one group, almost by accident, finds itself holding the right traits at the right moment: the dinosaurs. They are efficient runners. They breathe with air sacs that cool their bodies in hot climates. They stand upright, saving energy over long distances. They range widely across landscapes, newly emptied of competitors. When the volcanic skies finally clear, the ecosystems of the world are wide open. And into that space, dinosaurs step first cautiously, then magnificently. Over the next tens of millions of years, they grow larger, stranger, more diverse. Giant herbivores reshape forests. Predators evolve jaws and claws for every niche. Feathered forms take to the air, and the Jurassic world becomes a place of booming footsteps and deep, echoing calls. The Triassic extinction doesn't just remove life, it writes an invitation, and dinosaurs answer it fully. But this age, too, will end. Not yet, not soon, but inevitably, for the Earth's rhythm marches forward. Boom, collapse, rebirth. And in our next chapters, we will walk with those giants, watch their world flourish, and see the asteroid that ends it all. Chapter 6. The Age of Giants. When dinosaurs ruled a healing world. If you could step into the world just after the Triassic extinction, the moment the volcanic skies finally clear, you would find a planet trembling on the edge of possibility. The destruction has ended, but its echoes linger. Forests are sparse. Rivers run uncertain paths. The air feels different, as if the atmosphere hasn't quite settled back into place. And yet, in this uneasy quiet, something extraordinary is beginning. This is the dawn of the Jurassic. The Earth is warming again, slowly and gently compared to the violent swings of the past. Moisture rises from vast oceans, falls as rain onto continents, and feeds the growth of deep green forests. Ferns unfurl, conifers stretch upward, cycads and ginkgos form ancient gardens beneath towering canopies. The land is becoming a quilt of lush ecosystems, wetlands, river deltas, dense forests, sandy plains, each one shaping itself anew after the losses. Into this recovering world step the creatures who will define an era, not suddenly, not thunderously, but with quiet persistence. The dinosaurs. At first, they are still small, light, nimble, two-legged, barely larger than a dog or deer. They stay close to forests or scramble along riversides, taking advantage of open ground left behind by vanished species. But the world is changing in a way that quietly favors them. The climate becomes warmer and more humid, conditions perfect for the dinosaurs' unique respiratory system. Unlike most reptiles, dinosaurs likely possess air sacs, allowing for unidirectional breathing. Air moves smoothly through their lungs in one direction, delivering oxygen efficiently even in thick, warm air. This single biological innovation becomes a quiet superpower. It means they can run fast without overheating. They can stay active in environments that would exhaust other reptiles. They can move long distances to find food in still-forming ecosystems. Meanwhile, their upright stance, their legs positioned directly beneath them, instead of sprawling like crocodiles or lizards, gives them speed and endurance. Their bones are strong but lightweight, some even partially hollow, reducing the energy needed for movement. Add to this their sharp senses, good eyesight, agile balance, and the dinosaurs begin to explore new territory. Not just physically, but evolutionarily. Some grow larger, others grow longer. Still others experiment with new diets or new habitats. The world is open, and evolution is wide awake. By the Middle Jurassic, this quiet rise has become a transformation. Herbivores evolve into titans, brachiosaurs, with necks that reach high into conifer forests. Diplodocids, long as city buses, sweeping entire groves with their whip-like tails. Stegosaurs, armored with plates that shimmer red and orange when warmed by sunlight. These giants reshape landscapes. They eat forests into open plains. They carve pathways through dense vegetation. They become engineers of their environment, just as elephants and bison do today. Predators evolve in response. Allosaurus, powerful and cunning. Ceratosaurus, slipping through riverside thickets. early tyrannosauroids, small but growing smarter, faster, hungrier. The world becomes a living tapestry woven from footfalls and shadows, from the rhythm of giants moving through forests and hunters stalking the edges of herds. But dinosaurs do not dominate only the land, they touch the sky. A group of feathered dinosaurs, tiny, fragile, and curious, begin to experiment with flight. Their feathers, once used for warmth or display, become tools of gliding, then flapping, then soaring. The first true birds appear, delicate but brilliant, bridging the boundary between earth and sky. The Jurassic is not just an age of giants, it is an age of beginnings. Meanwhile, in the oceans, life is rewriting itself too. Marine reptiles spread, ichthyosaurs shaped like dolphins, plesiosaurs gliding with long necks or massive jaws. Their world is one of drifting plankton, thriving reefs, and deep, calm basins. The seas have recovered from the anoxia of the Permian and Triassic. The water is oxygen-rich again, currents flow, reefs stabilize, ecosystems become thicker with life. It is a world flourishing, a world healed. And yet, even here, the Earth's old rhythm hums beneath the surface. Boom, collapse, rebirth. For now, we are in the boom. Life is everywhere, on land, in the sea, in the sky. But deep inside the planet, tectonic plates continue to drift. Rifts expand. Subtle changes accumulate in the atmosphere. Volcanic systems shift. No one, no creature, no tree, no drifting ammonite could sense what the Earth was preparing. But the rhythm always returns. And after this age of giants, comes the age of endings. Chapter 7. The Shadow in the Sky. The Last Day of the Dinosaurs. If you were alive 66 million years ago, if somehow you could stand in a Cretaceous forest, beneath towering angiosperms and buzzing dragonflies, you would never guess that the world was about to end. Everything looks vibrant, healthy, timeless. Lush forests blanket entire continents. Flowers bloom in dazzling colors never before seen on Earth. Insects swarm, bees, butterflies, beetles forming the early symphony of pollination. Dinosaurs, now in their full glory, move through this living tapestry. Tyrannosaurus rex, the apex predator of North America, patrols river valleys rich with fish and turtles. Triceratops, armored with horns and frills, graze in vast herds. Ankylosaurs rumble through underbrush with clubbed tails ready for defense. Hadrosaurs, the duck-billed giants, vocalize in deep, resonant calls that echo like music across wetlands. The skies shimmer with pterosaurs, some with wingspans longer than a small aircraft. The oceans below teem with mosasaurs, sea turtles, and reef systems bright with life. It is a world thriving at the height of its complexity. But far above this planet, far beyond any eye or sense, something moves through space. A fragment of rock, 6 to 9 miles wide, traveling at over 40,000 miles per hour, faster than sound, faster than comprehension. The dinosaurs' world is about to pivot in a single moment. The asteroid enters Earth's atmosphere at a shallow angle, generating heat brighter than the sun. The friction is so intense that the air itself turns to plasma. Animals grazing on distant plains might look up at a sudden streak in the sky, a white, burning scar etched across the blue, and then return to feeding, unaware of what it means, because the noise hasn't arrived yet. Sound lags behind speed. And then, impact. The asteroid strikes the shallow seas near what is now the Yucatan Peninsula, in a place we call Chicxulub. In less than a second, rock turns to vapor. The Earth's crust ripples like liquid. A crater over 100 miles wide opens instantly. The energy released is more than 1 billion atomic bombs. Shockwaves radiate across continents. Earthquakes circle the globe multiple times. Mountains crumble. Tsunamis, thousands of feet high, sweep entire coastlines. Trees explode into flame from the thermal pulse. Animals on the far side of the planet are thrown off balance. Molten ejecta is blasted high into space, then rains back down hours later as fiery droplets, turning the sky into an oven. Anything exposed burns. Wildfires ignite across multiple continents. But the worst has yet to come. Dust, soot, sulfur, aerosols, vaporized rock. All of it rises into the upper atmosphere and spreads globally. Within weeks, sunlight dims. Within months, global temperatures plummet. This is impact winter. Photosynthesis stops. Plants die. Herbivores starve. Predators follow. In the oceans, plankton collapse. Coral reefs bleach and crumble. Marine reptiles vanish as food chains disintegrate. Dinosaur eggs fail to develop. Juveniles die before reaching adulthood. Even the mighty tyrannosaurs fall silent. By the time the skies begin to clear, a process that takes years, 75% of all species are gone. The non-avian dinosaurs, ammonites, pterosaurs, mosasaurs, countless plants, insects, microorganisms. The world that rises from this darkness is not the same world that entered it. But not everything is lost. Some birds survive, some mammals, some crocodilians, some amphibians, small, hidden, flexible, unnoticed. Just like the survivors of previous extinctions, they are not the strongest, not the largest, but the most adaptable. From them, a new chapter of life will begin. Chapter 8 inches, the wake of fire. Mammals and the quiet rebuilding of a broken planet. When the fires finally burn out, when the dust begins to settle, when sunlight returns to Earth through a dim, muted sky, the world looks nothing like the one before. Forests are gone, grasslands are ash, entire continents are scarred by soot and sediment. Yet in this vast silence, beneath fallen logs, inside cracks in the soil, in small pockets of forest that escaped the worst heat, life stirs. The dinosaurs may be gone, but the story continues. And the next chapter belongs to the mammals. They were always there, even in the age of giants. Small, nocturnal, scavenging, eating insects or seeds or roots. Some lived in burrows, some in trees, some in leaf litter. When the asteroid struck, their very smallness became salvation. They didn't depend on vast food chains. They didn't need huge territories. They didn't require specific climates. Many could survive on almost anything. Warm-blooded, insulated by fur, they could endure cold impact winters far better than reptiles. Those that burrowed were shielded from firestorms. Those that ate seeds thrived when everything else struggled. Now, with the dinosaurs gone, the Earth becomes a gallery of empty spaces, and the mammals begin to explore them. In the Paleocene world that rises from the ashes, mammals diversify cautiously at first. Tiny shrew-like insectivores scurry through recovering underbrush. Early primates leap between branches in warm tropical forests. Cat-sized omnivores forage near rivers. Hoofed mammals begin to evolve specialized teeth for new plants. Plants themselves transform. The extinction eliminated many ancient species, clearing the way for the explosive spread of flowering plants, which reshape entire ecosystems. As forests regrow, mammals adapt to them. As grasslands emerge, mammals follow. As rivers stabilize, mammals flourish near the banks. Within a few million years, the diversity lost in the impact begins to regrow, not the same forms, not the same giants, but new experiments. Some mammals become predators, some grazers, some climbers, some swimmers, some gliders. Evolution is rewriting life, not from scratch, but from a smaller palette of survivors. But the most remarkable change is happening quietly in the trees. Tiny primates, with grasping hands and forward-facing eyes, begin to experiment with depth, color, social structures, and long childhoods. Their brains grow larger relative to body size. Their sensitivity to sight and touch becomes more refined. These early primates do not know it, but they are setting the stage for something unprecedented: the evolution of cognition, culture, and curiosity. Far in the future, one lineage of primates will stand upright. Its hands will craft tools. Its eyes will study fossils. Its mind will ask questions about origins and endings. And its voice will tell stories like the one you're hearing now. All of that begins here, in the quiet aftermath of the dinosaurs' fall. Mammals didn't rise because they were destined to. They rose because the world changed in a way that happened to suit them. Just as dinosaurs rose after the Triassic extinction, just as amphibians rose after the Devonian, just as fish rose after the Ordovician, life builds its future from what remains. Extinction clears the stage. The survivors write the next act. Chapter 9. The Sixth Shadow. The Extinction. We are inside. 2000 Tunza. If you were a traveler in deep time, someone who could drift through hundreds of millions of years like a leaf floating down a long river, you would notice something unsettling about the present moment. It feels different. Not because the forests are silent or the skies are dark. Not because oceans have lost their color or continents have cracked open, but because the changes happening now are faster, much faster, than almost anything the Earth has seen before. Tonight, we step gently into the unfolding story of the sixth mass extinction, the one not written in stone yet, but in real time, in forests and oceans, and quiet corners of the world, where creatures disappear without headlines. To understand the scale of what's happening, we need to step back, to zoom out far enough that the rise of mammals, the appearance of primates, even the emergence of early humans, become tiny ripples on a vast sea of time. After the asteroid struck, and mammals began their slow ascent, evolution spread outward like light in newly opened space. Primates branched, apes emerged, hominins walked. Eventually, humans appeared not suddenly, but gradually, shaped by fire, community, curiosity, and the strange alchemy of thought. For hundreds of thousands of years, humans were simply part of the world, hunting, gathering, using fire, moving with seasons. We were a whisper in the ecosystem, not a threat. But as intelligence deepened, as hands crafted tools, as language allowed the sharing of ideas across generations, something remarkable happened. Humans began shaping the world, not just surviving in it. Fire cleared land, agriculture fed cities, cities built roads, roads linked nations, machines bent rivers and carved mountains, and technology magnified our influence beyond anything life had seen before. With that power came consequences. Species began vanishing, slowly at first, then faster. Some disappeared because forests were cleared for farmland. Some fell to overhunting. Some couldn't tolerate pollution in the air or water. Others were lost when climate patterns shifted faster than evolution could keep pace. The Earth has had 5 mass extinctions before. They took tens of thousands of years, sometimes hundreds of thousands. This one is unfolding in centuries, in decades, in human lifetimes. Scientists estimate that species today are going extinct at a rate 100 to 1,000 times faster than the natural background rate. Some biologists believe we may be losing dozens of species every day, many before we ever discovered them. But unlike previous extinctions triggered by volcanoes, asteroids, or global collapses in oxygen, this one comes from a creature fully aware of its actions, us. And that awareness is a turning point in the story of life. To understand how delicate this moment is, imagine the Earth's ecosystems as a vast web. Each thread is a species, small or large, common or rare. Some threads are thick, carrying heavy weight. Corals, bees, plankton, grasses. Others are thin, fragile, beautiful. When a single thread breaks, the web holds. When dozens break, it weakens. When hundreds break, sections sag. When thousands break, the tension redistributes until it reaches a critical point. What we don't always see is that our own survival is woven into that web. Forests, regulate air, wetlands filter water, insects pollinate food, soil microbes recycle nutrients, oceans absorb carbon, biodiversity stabilizes climates. When those systems fragment, the stability we take for granted begins to tremble. This doesn't happen with a bang, it begins quietly. A disappearing frog species, a bleached coral reef, a once common bird no longer heard at dawn, a forest that grows more silent each year. Extinctions accumulate like grains of sand sliding down a slope. The pile grows steeper. A single grain triggers a landslide. We call these tipping points. Once crossed, they do not simply reverse. Rainforests can become savanna. Rivers can dry into dust bowls. Ice sheets can melt beyond recovery. Ocean currents can shift irrevocably. We are not separate from these shifts. We are inside them. We are participants, not observers. Yet, the sixth extinction is unique in another way. For the first time, a species understands what is happening. We can name the problem. We can measure the damage. We can predict the outcomes. We can choose differently. No trilobite or dinosaur ever had that chance. And with this awareness comes responsibility. To protect forests whose roots stabilize not just soil but the climate. To restore coral reefs that nurture a quarter of marine life. To safeguard rivers that pulse through continents like veins. To preserve species not just for beauty, but because they are threads holding the world together. The sixth extinction is not inevitable. It is not a prophecy. It is a question. What kind of ancestors will we be? And as we step from this chapter into the next, we look not at the creatures who fall in times of collapse, but at the strange, resilient beings who always find ways to endure. Chapter 10: The Invisible Survivors, Extremophiles, and Life at the Edge. If you think of life as fragile, delicate coral reefs, trembling ferns, creatures needing just the right temperature or rainfall, then the story of extinction seems overwhelmingly dark. But Earth has a secret, a hidden reservoir of resilience far beneath the surface of ordinary life. These are the extremophiles, the beings that thrive where nothing else can. To meet them, let your mind drift into the strange corners of the Earth, places so hostile, so deadly, that they seem more alien than planetary. And yet, in all of them, life persists. Imagine plunging to the bottom of the ocean, deeper than sunlight can reach. Down here, pressure is crushing thousands of times greater than at the surface. Water is near freezing. Darkness is absolute. Then suddenly, a glow in the distance, a hydrothermal vent. Boiling water erupts from cracks in the seafloor, at temperatures exceeding 400 degrees Celsius, hot enough to melt lead. This water is rich in metals, sulfur, and toxic chemicals, and clustered around the vent, life blooms. Tube worms, bacteria, crustaceans, tiny organisms using chemical energy instead of sunlight. These creatures survive by chemosynthesis, breaking down inorganic molecules to fuel their existence. They thrive in what should be a biological void, a reminder: life does not need comfort, it needs opportunity. Now imagine a different extreme. Antarctica, a desert of ice, temperatures so low that breath crystallizes, wind carving snow like stone, darkness lasting months. Yet beneath the ice, deep in subglacial lakes untouched by sunlight for millions of years, microbes drift in cold, nutrient-poor water, slow, patient, alive. Some feed on minerals, some on gases dissolved in ice. Some operate on metabolic cycles so slow that a single generation may span centuries. Time barely touches them, and still they persist. There are lakes so salty they should kill every cell, pools of acid with pH rivaling battery acid, caves filled with poisonous gases, mountaintops blasted by UV radiation, radioactive zones where DNA is constantly shredded. And yet, in each of these places, life endures. Microbes repairing damage faster than radiation breaks them, algae surviving complete desiccation, rehydrating as if waking from sleep, fungi growing in nuclear reactors, bacteria living miles underground, feeding on chemical traces in rock. And then there is the tardigrade, barely the size of a grain of sand, 8 legs, a face like a tiny wrinkled bear. When threatened, it curls into a state called a ton, shutting down almost everything. Metabolism drops to near zero. DNA coils into protected bundles. The creature becomes a living time capsule. In this form, tardigrades can survive boiling, freezing, radiation, vacuum, even the void of space. A creature so small you could breathe it in, yet so resilient it can cross extinction after extinction unharmed. These beings tell a different story about life, one that is easy to forget when we focus only on the fragile, the beautiful, the visible. Life is not weak. Life is stubborn. Life is inventive. Even when oceans suffocated in the Devonian, extremophiles thrived. Even when volcanoes poisoned the Permian world, extremophiles endured. Even when the asteroid turned skies black in the Cretaceous, extremophiles waited. And even now, in our changing climate, they persist beneath deserts, ice caps, and deep crustal rock. If extinction is the erasing of complexity, extremophiles are the ink that never dries. They hold the simplest, oldest blueprints for survival, and they become the architects of life's rebirth after every collapse. From them, the next ecosystems grow, and from their example, we learn the quiet truth. Life does not cling to comfort. It clings to possibility. Chapter 11. Rebirth. How evolution rebuilds after every collapse. Every extinction leaves behind ruins, ecosystems emptied of their architects, food webs snapped, diversity thinned like a forest after wildfire. But extinction also leaves something else. Space, a blankness waiting to be filled. And evolution responds with creativity. To understand this, imagine a forest after a burn, charred trunks, ash-covered soil, silence. Then, weeks later, tiny shoots. Months later, grasses. Years later, young trees. Decades later, a forest reborn, not identical, but new. Now stretch that image into geological time. Mass extinctions reset not just forests, but the entire world. After the Ordovician, survivors rebuilt oceans with sturdier shells. After the Devonian, fish evolved new forms of jaws and limbs. After the Permian, reptiles exploded into unimagined shapes. After the Triassic, dinosaurs rose toward dominance. After the Cretaceous, mammals leapt into open ecological space. The pattern is always the same. Collapse, vacancy, innovation. Extinction pulls down the old scaffolding. Evolution lifts up the new. Why does innovation flourish after crisis? Because stability, for all its beauty, is restrictive. When ecosystems are full, niches are occupied. New forms struggle to compete with established giants. But when the giants fall, the world becomes a laboratory again. Suddenly, empty niches invite experimentation. The skies open after pterosaurs fall, birds diversify. Reefs collapse after corals vanish. New builders emerge. Predators disappear, prey evolve into new defensive strategies. Forests, thin grasslands spread, changing herbivores forever. Oceans reset, plankton evolve fresh architectures. Life becomes bold when the world resets. The first mammals were small, inconspicuous, nocturnal. After extinction, some became giants. Others took to water. Some returned to trees. Some sped across plains. All from the same few surviving ancestors. And here is a deeper truth. Evolution is not rebuilding what was lost. It is building on what remains. Each extinction pushes life into directions previously impossible. Without the Permian collapse, dinosaur ancestors would never have risen. Without the Cretaceous impact, mammals would never have flourished. Without ancient oxygen crises, complex life might never have evolved at all. Extinction is tragedy, but it is also transformation. It is nature's brutal reset button, rewriting the story of Earth again and again. We often imagine life as a ladder rising from simple to complex, from small to large. But life is a spiral, each loop shaped by collapse, each turn bringing new possibilities. When seen from far enough away, the pattern becomes almost peaceful. Boom, collapse, rebirth. Boom, collapse, rebirth. Earth breathes in cycles far longer than civilization, longer than species, longer than memory, and we are living in just one moment of that breath. Chapter 12. Borrowed Time. What this moment asks of us. The earth feels calm tonight. Forests breathe slowly in the dark. Oceans sway with the pull of the moon. Cities glow with artificial constellations. People move through streets unaware of the deep time beneath their feet. But beneath this calm is motion, tectonic plates shifting, ice melting, oceans warming, species migrating, forests drying. These changes are slow enough to ignore day to day, yet fast in the scale of Earth's rhythms. We live in a time between endings, past the last great extinction, before whatever comes next. A narrow window, a fragile moment, borrowed time, and like all borrowed things, it asks something of us. Not perfection, not guilt, but awareness, an awareness of scale. That our lives are brief flashes on a 4 billion-year canvas, an awareness of connection, that the air we breathe, the food we eat, the water we drink, all depend on ecosystems older than civilization itself, an awareness of choice, that unlike trilobites or dinosaurs, we can adjust our impact. We can protect forests instead of clearing them. We can restore reefs instead of watching them fade. We can rebuild soil instead of depleting it. We can guide technology toward healing instead of extraction. The earth does not need us to be perfect. It needs us to pay attention, to listen when rivers thin, to notice when insects vanish, to care when a forest falls silent, because every species lost narrows the future, and every species saved expands it. We ask, will humans survive the next extinction? But the real question is gentler, deeper. What version of the earth do we want to hand forward? One filled with raptors and rivers and wild forests, buzzing wetlands and glowing reefs, or one diminished, holding only the hardiest scraps of what once was? We are not the first species to face collapse, but we are the first to understand it. And that understanding is a form of power, a soft power, a mindful power, a chance to choose. If extinction is a rhythm, then so is renewal. If collapse is a phase, then so is recovery. If the earth begins again after every ending, so can we. And as we close this chapter, this long journey through fire and ice, through oceans without breath, and skies turned black, there is one last truth to hold gently. You are here, alive, breathing in a moment that billions of years have shaped. A moment full of uncertainty, but also full of possibility. The earth has begun again many times. And now, in this borrowed moment, it is our turn to decide how the next beginning will look.